to Jan-Åke.
Thank you, Lars. We are super excited, breaking a small record here for our webinars. So this is being recorded for YouTube, but it's also live streaming on YouTube as of right now. And with all counts made, we should be passing 200 registrants, which is exciting. And for this, we have invited some external hosts. So if we take next slide, Lars. This is the subjects of today's Connecting the Dots. So we are focusing on positioning, both the challenges on the tech side, but also trying to zoom in a bit on the commercial aspects of what kind of values we can bring in with the help of positioning. So today we have James Tidd from Swift Navigation and Henrik Sim from Sigma Connectivity and Johan Wallin from Husqvarna. Before we start, I just want to give a brief update on what happened to WSI in case you've missed it. We were acquired by Sigma Connectivity as of September last year, and we have, compared to before, we have now become tremendously big in terms of capacity. So we are now 600 plus colleagues spread out in Sweden, over Lund and Linköping as well, and in Denmark, US, and Poland. We have access now to a world-class 5G labs as well as resources, some 4 years experience of working with 5G. We also have access and resources for advanced audio, and also adding cloud and app capabilities to the in-house competency in the projects we run. By the size and by the clients we have now, we have also even better supply retention than we used to have before. And also the dot above the I, we launched a couple of weeks ago, WSI Engineering, which means that we in the Stockholm area also now provides on-site consultants in Stockholm. If you want to know more about this, pinch into the WSI site on LinkedIn and look for Emily Garcia, who's heading up that part, or just call into your regular WSI friend and he or her will help you to find Emily. Enough about WSI, and let's put the first speaker on stage. Take it away, James.
Okay, thank you. So yeah, I'll introduce myself, Swift Navigation, and tell you a little bit about precision GNSS positioning and the state of the art of that technology as of today. So I work for a company called Swift Navigation. Our mission is really focused at autonomous vehicles and to enable them to achieve the efficiencies and safety that they promise through centimeter accurate absolute localization. A little bit about the company. So we have over 3,000 customers in various different vertical markets, from precision agriculture, automated combine harvesters, right through to autonomous vehicles, rail and delivery robots, and all of the autonomous markets that you can imagine. We are based out of San Francisco, and our main focus is the automotive market, so self-driving cars or more near-term high levels of advanced driver assistance systems. We are predominantly a satellite positioning company, and we've been around for about 9 years, and we're coming up to 100 people globally, from Australia, San Francisco, and quite a presence in Europe as well, having resources where our customers are. So positioning is what we're talking about today. And when it comes to precise positioning, predominantly for the automotive market, it enables an awful lot of use cases. I've mentioned advanced driver assistance systems and autonomous navigation, but there's other use cases such as geofencing. That could be to change the drivetrain of a vehicle from diesel to electric when you enter inner city areas. Or it could be tolling or other functionality which changes depending on where you are. And there's some of the more familiar ones like navigation, GNSS or GPS as it's often called, is commonplace now in our mobile phones, in our cars, and in our daily life. More so than most people would understand. It's often used to timestamp financial transactions, so it's ubiquitous in everyday life. I'm going to talk a little bit about the different technologies that autonomous vehicles use, predominantly focusing on visual and radio-based positioning technologies. GNSS covers a wide area in this spectrum of accuracy versus penetration or environment. GNSS, as everyone knows, prefers an open sky to get the performance it requires. And GNSS is one of the ones that offers really global performance. So wherever you are on the Earth, GNSS will perform really quite well. What I'm going to focus on today, though, aside from these other technologies, is precision GNSS. And that's where we get down to the centimeter levels of accuracy. And of course, if you achieve a higher accuracy, you enable all of these other use cases. But precision is really something for less dense urban environments, so highways, rural, where there's more of an open sky. So the use cases that people want to achieve with autonomous vehicles vary greatly. The one that springs to people's mind often is that a taxi will pick you up and drop you off at your destination. But there's autonomous trucking for long distance travel. There is some smaller features like summon and autonomous valet. So your car will park itself and return to pick you up from your front door. And there's a few, I call out cooperative perception and cooperative awareness here, which are two connected vehicle use cases, cooperative awareness being sharing information about the vehicle so that other vehicles can avoid you. And cooperative perception is where you share sensor data from the vehicle. So you're able to see around corners effectively, or use the sensors of another vehicle to improve your awareness as an autonomous vehicle. And a lot of these are quite common. It's probably worth calling out augmented reality, because that's becoming more prevalent. And to augment the world around you, you really have to have great awareness of where you are with respect to the 3D objects around you. So high definition maps, positioning really supports augmented reality and the use cases achieved there. So GNSS sits across a lot of these use cases as an enabling technology. It doesn't work very well indoors, but it really achieves quite a lot of coverage of key use cases for autonomous vehicles. So how do we go from GNSS as a technology which we are all familiar with today down to something which achieves centimeter level accuracy? Well, we have two products which achieve this: Starling, which is a piece of software that runs in a vehicle, and Skylark, which is a correction service. To achieve high accuracy and high availability, we integrate inertial sensors into the positioning engine. And we also interface with a conventional GNSS receiver, which tracks the signals from the sky. So we get ranges from the GNSS, inertial data from the sensors, fuse that together, and we achieve absolute position, velocity, attitude, and heading. Sounds very simple, very brief overview of the architecture. It's Skylark where a lot of the processing is. And this is Skylark. This is where we have rolled out a reference network of GNSS receivers, each of them measuring the satellite signals that are transmitted. They are then transferred to Skylark, which is a cloud-based correction server that calculates all of the errors in the GNSS satellite transmitted signals and sends them out to the Starlink positioning engine in the vehicle so that it can correct for them. What I'll do now is go through some of those errors just to give you a feel of some of the processing that Skylark has to do to achieve that centimeter level accuracy. So there's spatial and temporal errors with the satellites. They're in the wrong place in their orbit, and they have the wrong time. As the signals travel from the satellites down to the Earth, they have to travel through both the ionosphere and troposphere, which cause advances and delays in the signal, depending on which part of the atmosphere it is. And then the local environment. There's noise, there's interference in the GNSS bands, and there's multipath, where the signals bounce around off local buildings and other vehicles. And so we have to take care of all of those. And there are some more which we have to take care of. Apart from the signals being transmitted and having some error, there are some more subtle errors, maybe calling out predominantly that the Earth we live on isn't a perfect sphere, and it isn't static. It rotates, and it changes its shape depending on celestial forces. So the sun's pull on it and the moon's pull on it. And so we have to take into account both the hardware or engineering, electrical engineering errors, atmospheric errors, but also celestial forces on the Earth. Working in this absolute frame really introduces quite a lot of interesting problems, having to deal with the fact that we're on this massive ball spinning through space with other large celestial bodies having effect on the shape and size of our planet. And when you get down to centimeter level, these things start to really impact. And that's what we model in Skylark. We model them, we pass the models down to the user, and they can correct for it. So once we've got it working, we've estimated all of these errors, and we have done our best to ensure that we meet the accuracy. For autonomous vehicles, it's not only good enough to make sure that it works, we have to make sure that it doesn't break. Maybe particularly in Sweden, there's a culture of safety, as maybe there should be all over the world. And part of our unique proposition is that we ensure that the positions we deliver are very safe. To ensure something's safe, you have to make sure that it's functionally safe. So if something goes wrong by accident, it doesn't lead to a hazard. If something goes wrong by intent, so there's a security threat, someone's tampered with the system, whether physically or through RF or radio frequency. And then finally, performance. So on the right here, I show kind of to build a safety house, you have to take care of these three things, because one weak pillar and the safety case really falls apart. The last is performance. So not only do we have to make sure it's safe, we have to make sure we understand how accurate our performance is. And this slide tries to describe that we're now looking at, as you can see, 99.99999% of the time, we will give a bound which indicates how accurate our position is, and really that we will never have a position error that's outside of that bound. And that's really key, because not only do you want to know where your vehicle is, you want to know where every corner of your vehicle is, and that it's in the right lane, and that it's not going to collide with another vehicle. So in summary, all of these errors have to be taken care of. There's an architecture that's spread across many continents in order to estimate the orbit parameters and time of the satellites. And it all comes down to making sure that not only can we give you a very accurate position, we can guarantee that that position is in the right lane or is on the right side road of a motorway. Because without that trust in the estimate of position, it's quite worthless to an autonomous vehicle. So that concludes my presentation now. Very quick overview of what I consider to be quite a complex subject, but happy to take any questions if you have any.
Thank you, James. Thank you very much. And I hand over the word to Daniel to moderate the Q&A.
Yes, I have a question. What about smaller vehicles like those little e-bikes, for example?
So mobility scooters or electric scooters, this technology works equally well. The power and price point is somewhat different in those platforms, and antenna positioning can be more tricky because there's a human rider that's over the main body of the vehicle. They're often used in more dense urban environments, so that's more of a challenge for GNSS, but there's nothing that fundamentally prevents using high precision GNSS in those applications.
How well are you handling urban environments?
So our integration with IMU and wheel odometry really helps us there. And extra signals are, the satellites have 3 key frequencies. Using those extra frequencies really gives you a benefit for multipath mitigation, which is the key problem with dense urban. We actually use the carrier frequency that's transmitted, which is also more immune to multipath than conventional GNSS that uses, without being too detailed, uses the code section of GNSS. So using multipath gives you more immunity. Tunnels are still a problem where we can't see any satellites, but that's when our inertial integration helps us. So for a GNSS receiver, we're really good for dense urban, but it's a challenge for any, let's put it this way.
I have another question here. Is where are services available so far? US only, or are you entering the global market?
Sure. So the US network has been up for a number of years now. We're rolling out in Europe with our partner Deutsche Telekom. You can imagine this is quite an undertaking to roll out a reference network, and cellular companies are used to rolling out infrastructure in that way. So we've partnered with Deutsche Telekom to roll out in Europe, and plans are for Asia by the end of this year to have large coverage over there in the key markets. And we have support in Australia and other places as well, but the key safety product is rolling out. It's in US, it's in EU, and it's coming in Asia later this year.
One last question here. What's your business model looking like?
So we sell 2 things. We sell Starling as a piece of software that runs in an ECU in a vehicle, and we sell Skylab, which is a service. So that's more of a subscription-based model as opposed to a license-based model for the software in the vehicle. They're the 2 products we have. We have some hardware products that implement Starling in a box, Duro, Pixie, and they're sold as hardware products, but the service is a service model and the software product is a license model.
Okay, thank you. For the rest of you asking questions, please come in with them and we're going to try to answer them as good as we can.
Thank you very much, James and Daniel. And with having that said, I'd like to hand over the presentation to Henrik, who will talk a bit about his area of expertise. So Henrik, the floor is yours.
Thank you very much. Just going to share my presentation.
Great, looks great. Good luck, Henrik.
Thank you. Thanks for having me. So very short introduction about myself. I've been working with radio technology for more than 20 years. I've been doing a lot of cellular design through my career. And here the last 7 years been focusing a lot of focusing a lot on other radio technologies like ultra wideband, Bluetooth, Wi-Fi, and also GNSS systems. Currently, I am a IT system specialist at Sigma Connectivity. And today I'm going to talk about very low power positioning technologies for outdoor wide area locations. So before we dig into it, I want to talk about the alternatives first. So if your specification is saying that you need better than 20 meters accuracy, then there is no other choice than using GPS. Well, it's also called GNSS, but you all know that. But if you can live with an approximate position, then there are technologies like cell location. And I will be talking about both of these two here. So first technology out I will talk about then, it will be GPS. And as always, when choosing a GPS or GNSS chip, you have to do the right choice from the beginning, because there is a lot of old chipsets out there, and the old ones use a lot of power, and that's because the lithography process has improved over time. So the newer technologies and newer chipsets are really, there is a large variation in power between old and new chipsets, let's say it like that. And also the algorithms have become smarter and more efficient over time, which also lowers the power. And then there's a simple trick to go low power. If you're going a little bit more low power, if you're willing to trade off a little bit from the accuracy, and that is disable other satellite systems like GLONASS, Beidou, and Galilei, because you only gain about 0.5 meters accuracy having those activated. But disabling them and only have GPS left saves you up to 25% of the power. So, but the real area where you can save power is by going away from the continuous tracking mode and only take position updates every hour or every day. Or why not doing it when something happens? For example, the device moves, as a motion activated tracking. The downside is that you very quickly lose the ephemeris and the almanac data, which James talked about, which contains the information about time dilation and atmospheric weather and Earth's and the satellite's exact position and so on. This data is required for doing a fast fix with the GPS. If you don't have this data here, you will have to use up to more than 30 seconds to find your position. And some modems we also have some kind of second gear they put in, and they use even more power when they go down in a cold start mode. And reading through the specs, you can see some modems will use up to 40% more compared to tracking mode. So the bottom line, you really don't want to lose ephemeris and almanac data, because that is bad for power consumption. So what can you do? Well, one technique is doing as our smartphone does. Assisted GPS. That means you download the almanac and the ephemeris data from a server. And when you have that, you can start up the GPS in about 1 second in a good environment. Of course, if the signal conditions are not so good, then it will take longer time. If we take an example, compare this with a cold start of a GPS, then it will cost you about 2150 millijoules to get a GPS up and running if it has no clue about the satellites above. Comparing that with downloading 1 kilobyte of almanac and ephemeris data from a server with a narrowband IoT modem, that will take 500 millijoules, and then using 1 second for getting the fix for the satellites. You save 75% using assisted GPS. So bottom line here, not only are you getting a faster fix, you also save huge amounts of power. You can download almanac and ephemeris data up to 35 days in the future. If you want to go even lower in power, then you have to look what's happening inside the GPS module and what's consuming the power. So the most power consuming processes in the GPS is the signal processing unit and the position estimate. It's a very complicated math to calculate where you are and compensate for all the inaccuracies in the satellite and the atomic clocks and everything. So by piping out the raw signal data directly from the signal capturing unit in the GPS and compressing that and sending that up to the cloud, you can save up to 50% power compared to assisted GPS. But there's a downside that it's not all chipsets allow you to do this. And then you have to have a cloud service where you can do this processing in the cloud. There are very few companies that provide this. So far, I've only found 2. So that was my last slide about precise low power positioning. And next I want to talk about is approximate location. So you have everybody have most likely seen this when you turn on Google Maps on your smartphone and it has no clue about where it is and what satellites are above. Then it uses cell tower ID fingerprinting mode to calculate its position and displays that as a large circle on Google Maps. And you're inside that circle somewhere. And that's basically the phone just collecting cell IDs from all the radio access technologies and all the bands and sends that up, for example, to Google Locate Cloud, where it compares that cell ID pattern and returns back your position. There's no guarantee how good or how bad your position is, but usually works pretty good, especially inside cities. Out in the countryside, the accuracy is, well, really can vary a lot. But this is a smartphone. How about a simple narrowband IoT connected device, battery driven, only using a single band to save power? The principles are the same. The device listens for the neighboring cells and the serving cell and sends that list to Google Locate and or another server and spits out the position. So principle the same. Accuracy is not so good since you have very few base stations. But the very, very good thing is this process is for free because the cellular modem has to do this anyway. This is part of being connected to the cellular network. It has to keep track of neighboring cell and serving cell to understand if it's using the right cell. There's a way this can be improved a bit more, and that's called reference signal time difference. That's basically using the fact that LTE network is sending reference signals from every base station at the same time. By measuring the time difference of arrival of these reference signals in the device and sending that data together with the cell IDs where these signals came from to a cloud service, which has knowledge about where these base stations are, it is possible to trilaterate the position of your device. However, this requires that you have better than 100 nanoseconds synchronization of your reference signals, and that can only be achieved with base stations that are equipped with GNSS time synchronization units, which not all operators have, at least in Sweden. In US, it's more common than that they have that. It also requires that the cloud service providing this service has exact knowledge of the base station. And that is not, there are not so many operators that are willing to send the information about exact where their base stations are, and at least not in Sweden. They're kept secret where they are. But at least this is a very promising technique, and we'll once the operators or update their base station to 5G, then they will definitely have this GNSS synchronization of reference signals. that was my last slide.
Thank you very much, Henrik. Quite
Super
interesting.
interesting.
Yes, hand over the Q&A to Daniel.
Yes. So what's the life expectancy of a product like that on the picture running on a single AA battery?
Well, everything depends on the position update rate. So if you're going for once a day, you can achieve several years on a AAA 2 times AAA batteries.
So, but if you would estimate something like once every hour, where would you end up in a rough estimate?
I mean, you're gonna end at a bit over a year. On AAA 2 AAA batteries. But it depends if you're using the assisted GPS or using the post-processing process where you send the raw signal data up to the cloud. It's definitely much cheaper power-wise to send the raw data to the cloud and do the computation there.
Oh.
But the drawback of that technology is that you have very few companies that can provide this service, but there are some.
Okay, thank you, Henrik.
Welcome.
Thank you very much. And having that said, I'd like to hand over the word to Johan.
Hello. Let's see if I can get some picture as well.
Yes, we see you.
Brilliant. Okay. Hey everyone, and my name is Johan Wallin. I'm Vice President for Aftermarket and Connectivity at Husqvarna Construction. A few words about Husqvarna Construction. We are a company addressing professional users of tools and equipment and solutions working in the concrete business, you could say. So that's where I am. A few words about my history. I started my career with a degree, a master's degree at Chalmers University, and has then after that I worked within the telecom industry, rolling out GSM and working with telecommunication until 2002, when I joined the consultancy company. Where I worked with supporting other industry sectors with communication solutions. And I was in that position until 2018 when I joined Husqvarna. I have a true passion for emerging technologies, and I really like to see how you can create value to people and business using this. Okay, if we move forward, let's see if I can get the slides to move as well. There we are. What about the construction industry? Yeah, it's one of the largest sectors in the world, actually, with more than 100 million people employed. When it comes to digitalization and technologies, it's one of the least advanced sectors when it comes to digitalization. This is a study that was done by McKinsey, and I think it's still valid. It's a very traditional business. People are still using paper and pen in many places to communicate, and that is really a big difference if you compare to telecom and automotive, where I have spent my time previously. And this is of course something that will change. There is drastic shift ongoing at the moment, and that is not so strange, because if you imagine a construction site where you have hundreds of people that are cooperating, doing work together, and the productivity gains from better ways of communicating and using digital tools, it's really a good thing. But this will of course require people to change, and you have to adopt and embrace this type of new technology. And that's why we have created this unit that I'm heading in Husqvarna, because we believe strongly that this is a transformation that is needed and where we need to follow. If we then dial in specifically to positioning, then we can ask the question, what problems are there to solve in this industry and what benefits to gain? And as the previous speakers talked about, there are quite a lot of things to think about and address. I have come into a number of different areas where you can dial in here, but I have pointed out a few cases that I think is important, and also addressing different aspects to consider. So let's start. I don't know if you have seen this kind of situation that is shown on this picture. A construction machine, a generator or a compactor or something hanging in a crane while the construction site is closed and no one is working. It looks quite kind of strange, but it's not so strange, because the reason for it is obviously that they are trying to prevent theft. And theft is really a big problem in construction. A National Equipment Register made a study, and they estimated that the average value of stolen equipment was between 300 million and $1 billion US. And of this material or these machines, only 20% was recovered. So obviously there is a lot of money to save if you can keep track of the equipment and detect problems before they occur. There are other studies as well in US regarding construction sites, where they show that about 20% of the time is wasted searching for tool and equipment. And considering the size of this industry, that is also a lot of money. So tracking equipment has a great value, and it is something that clearly a lot of companies in this industry are focusing on. But there are problems to consider, and there are different requirements depending on the type of object you want to track. As it has been pointed out, depending on what kind of equipment you're selecting or using, you will have a different result. And therefore, when we look at this and thinking about these things, it's a lot of trade-offs you have to think about. For this type of use case, I mean, it must work both outdoor and indoor. You have to be able to handle it on larger vehicles where you can maybe reuse technology from automotive, but you must also be able to do it on handheld devices where the cost, the power consumption, and the size will be, you have limitations there. Precision here is not super important. Of course, you don't need to know fairly well where you are, but not in super detail. 10 meters would be, maybe up to 50 meters would be okay. And frequency not so critical either. As long as you can get accurate updates every 5 minutes, it's probably okay. And you should also be able to run on a battery for at least 96 hours or 4 days in order to be able to follow equipment if they are moving. So this is one area where you can see the use of positioning. If we dial into the next area, this picture is showing, if you're from Stockholm, you probably recognize it. It is the construction site Urban Escape that has been ongoing in the city center. And one thing that has changed drastically the last 10 years, I would say, in construction is the possibility to actually build and construct freely without taking considerations to the environment. And when you are in an urban area here with the, and in this case, in the city center, it is a lot of complications related to taking in and moving out goods. And in this specific case, they actually established a quite sophisticated scheduling tool where you were allowed in a certain time slot, and if you missed it, you had to wait because there is no way to be able to handle all the traffic otherwise. So with this type of solution, it really requires planning, and you need to have a fleet management system. So here you have another case where you need positioning. Here you're more outdoor, there are larger vehicles. Precision is not super important because you have a driver that will control the vehicle, but you really need to have accuracy or frequency need to be high, and therefore you will consume more energy, but normally these vehicles have they are running, so I think that you have power continuous. So that is not an issue. But this is another area where positioning is also impacting the construction industry. And then I would like to take the last example I want to point out, and that is touching upon the James area where we talk about automation and self-driving machines. It's a completely different area, and it will definitely have a big impact long term to create automation, especially for work tasks where you take long time and require skilled manpower. And you have an example here with troweling, which certainly will be an area where things will happen, floor grinding, but there is a lot of things where this can be used. But here you have completely different requirements than to consider. I mean, first of all, it's not only outdoors as here, you will also have indoor situations. Normally there are larger vehicles, but you can question that long term if it will not change. But here the precision is, as James said, less than 2 centimeters. You really need to be able to know exactly where these vehicles are or these machines are, since it can be quite dangerous if they would run away from you. So here the position information, you need it per milliseconds to keep track. And from a powers perspective, I don't see here is a big problem because they will most likely be battery driven, and you will be able to have a power station or charging station related to it. So it's a different case. But if we then conclude and just trying to summarize, there is of course a lot of other areas where you will have positioning use cases to address, but these were 3 examples of areas where we are currently looking into and expecting to move forward. And what is then important? Yeah, clear value. You can see there will be different requirements on the machines, so we have to consider different technologies, and there are many different aspects to consider building these kind of solutions. And with that, I hand over back to you, Daniel.
Thank you, Johan. Great. We have been burning time like crazy, so the potential questions going to be answered online afterwards. And I forward now to Jan-Åke to wrap this up.
So when Janoke is trying to unmute himself, we are, as Daniel said, on the end of the agenda. Thank you very much to all speakers, and word over to Janoke.
Yes, thank you all, especially to our guests who shared their insights and knowledges. As we said in the beginning, the complete YouTube video will be available afterwards if you joined late. And if you have any other concerns or questions, do not hesitate to come back to either me or Daniel or your other friends at WSI. There are several old episodes of Connecting the Dots also available on our YouTube channel. And I can already now tell you that a month from now, in the next episode, we will have the CTO of Sigma Connectivity talking and explaining more about 5G and the challenges and the opportunities that comes with 5G. So thanks a lot to everyone, and looking forward to seeing you the next time again.
Indeed. Thank you very much. And with that, we call it the wrap. Thank you very much, everyone.